So a binomial distribution is a probability distribution with two different parameters. The parameters are the number of trials n and the probability of success. P. So basically a binomial is an experiment that you're doing over and over and over and over and over again. Like somebody is shooting a hockey puck at a net 20 times, and they want to know what's the chance they get 10 of the shots in, if the probability of getting a shot is 30%. So what we require is the probability to be constant for each trial. For example, throwing a coin. The probability is always a half. Or getting a 2 on a dice. Probability is always 1/6. Okay, so each of these trials has to be independent. We can't have the probability changing depending on the first event. And each of these trials has only two possible outcomes. You either get it, success, or you don't, failure. In other words, it's either a yes or a no. So just like bicycle or bicentennial, when you see the prefix "di" in any English word, it means that there's two options. So a binomial has to have two possibilities. Either you succeed or you don't. Now, if you're tossing a dice has 6 possibilities. You can get a 1, a 2, 3, a 4, 5, or a 6. But even though it has 6 possibilities, we can model this with a binomial. For example, you want to know how many 5s you get if you roll a dice 20 times. So then the success is getting a 5, and the failure is getting 1, 2, 3, 4, or 6. All the other numbers. They can all count as not 5. So an example is like the probability of rolling a 5 versus the probability of getting not 5. Not rolling a 5. So rolling a dice can be an example of a binomial. The probability of failure is the opposite of probability of success. So the probability of success is P. Probability of failure is 1 minus P. Because the sum has to be 100%. And sometimes we call this letter, we call it something else, we call it Q. It's the probability of failure. And Q and P add up to 1. So as an example, Annie is shooting a gun. In each round she's got 3 shots, and the probability that she hits any shot is 1/4. She is not very good. It's probably a long distance shot. We can draw a table for the random variable x and the possible values of x. So we can do this just like we did last time. So she has 3 shots, and we're saying that X is the number of hits. In 3 shots. So what are the possible values? 1, 2, or 3. Anything else? Yeah, she could totally miss. So she could get all her shots, or she could miss everything. So we've got 4 different possibilities. Now to find the probabilities for each of these, we can make a tree. Oh boy. I might have to draw this really small. So to make this tree, we're going to break it up into 3 different branches. The first shot, the second shot, and then the third shot. So the first shot, the second shot, and then the third shot. Okay, so you need enough space to draw that tree. I'll try to move it up. The first shot she can either hit or miss. The second shot she can hit, miss, hit, miss. And the third shot she can either hit, miss, hit, miss, hit, miss, hit, miss. Hit, miss, hit, miss, hit, miss, hit, miss. I'm really, really glad that she's not shooting 10 times. You can see these trees would get big really fast. The chance that she hits is 1/4. So the chance that she misses is 3/4. She is really bad. Oh. But even those Olympic athletes that do that shooting thing, where they have to like run or cross-country ski and then go on the ground and shoot, they don't always hit the center. And they're Olympians. Yeah, this is not very well defined. So the chance that she hits all 3 is just 1/4 times 1/4 times 1/4. And I'm going to write that in factored form. I won't actually change that to a probability, just so that we can see some of the patterns here. I have 1/4 to the power of 3. How many ways can she get 2 hits? Let's see, we've got this branch, hit, hit, miss. Or hit, miss, hit. Or miss, hit, hit. So there's 3 different ways that she can get 2 hits. So the yellow one is 1/4 to the power of 3. The green ones are 1/4 times 1/4 times 3/4. Or 1/4 times 3/4 times 1/4. Or 3/4 times 1/4 times 1/4. Okay, so all of those have 2 hits. So they have 2 1/4s, and they have 1 miss. So they have 1 3/4. It's binomial theorem. And there's 3 ways that we can do that. We put the 3 in front. Okay, so this represents a hit. This represents a miss. We've got 2 hits and 1 miss. And 3 ways, 3 branches of the tree that can make that. Okay, so to get 1 hit, we can have hit, miss, miss, hits the first shot, hits the second shot, or hits the third shot. So this one also has 3 ways. 1/4 represents the hits. We have hit happening once and miss happening twice. Okay, so for each of those blue lengths of the tree, we're going to have 1 1/4 and 2 3/4. So we have 1 hit, which is 1/4, and 2 misses, which are both 3/4 probability. Do you see how the binomial theorem is coming out here? And how it makes sense? So then what do you think for 0? Yeah, you're having 3/4. That's a miss. And that has to happen 3 times, the power of 3. And there's only one way that we can do that, which is the very bottom of the tree. 3/4, 3/4, 3/4. 1 3 3 1. It's the top row of, or the fourth row of Pascal's triangle. 1 3 3 1. Isn't it beautiful?
Nice abstraction.
But it's all coming together. I mean, it's like connecting, expanding binomials, Pascal's triangle. If you want to find out how many pizza toppings you can have on your pizza, given a certain number of possibilities.
Two statistics and probability every time you order pizza.
So if you want to show that something is binomial distributed, we have a method of showing that, just a notation, and we're just saying that x resembles b for binomial. And we can change n, and we can change p. Okay, so the example above resembles, approximates. X can be modeled using. In the example above, we would have binomial, and n represents the number of trials. So that's how many times we tried. So in the example above, we tried 3 times to see if we could hit. So n would be 3. And p represents the chance of success. And we were looking for if we could possibly hit. So the chance of success would be, what's the chance of hitting? So that would be 3 1/4. B represents binomial. And binomial just means that there's 2 possibilities, either you get it or you don't. So now the cool thing is that the probability for any one of these different x's is the number of trials, choose r, times the probability to the power of r, times the probability of missing to the power of n minus r.
So cool.
This is exactly the binomial theorem. I can write it that again. The Q is just the chance of losing, the chance of missing. So this is exactly how you'll see it on your formula sheet. I think on your formula sheet they usually write choose using like NR, like this, and choose R.
So is the P, what's the P then? The other P.
The little p is the probability of getting success.
The large P though.
Oh, the big P, that's representing the probability of the random variable.
Oh,
So that's from last class.
no, on the calculator there's 2 P's, isn't there?
NPR and NCR?
Yeah, NPR.
Oh, that you haven't learned.
Oh, okay.
I can explain that later. Okay, so breaking this down, the NCR is just how many different ways or how many different branches of the tree. p to the power of r is like the number of hits, or the number of successes, and the q to the power of n minus r is just the number of misses. So the probability of miss to the power of how many times you miss it. Okay, so that's what the parts of that equation are representing. So we'll do some examples because the equation looks really complicated, but the examples are not actually so bad. And you can always get this on the video on YouTube if you miss any parts. Okay, so on the back side, we have the example that a fair coin is cost 10 times. We want to find the probability that we get exactly 6 heads. Now, if you're trying to make this into a tree, can you imagine? We're talking, this is 3 tosses, 4th toss. The tree's going to have 1,024 branches. So we're not going to make a tree. This is the reason why we've got the formula. So we don't have to have a tree. So we want to find the chance that we get 6 heads. First, we need to know, what's the chance of getting heads? 1/2. Then we need to know how many heads we want. Quite the tree, right? Question mark. So basically, what we're looking for is we're looking for 6 heads. Head, 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 and then how many tails?
4 tails.
4 tails, because we're tossing the coin 10 times. Okay, so each of these heads represents a probability of 1/2. Right? So we need how many halves? 6. And then we need to know what's the probability of getting tails. Also 1/2, which is the same as 1 minus 1/2. It's the opposite probability. I'm just using the same terminology as I do in the formula, but you could just write the number 1/2. So we need the tails probability to happen how many times? 4 times. Okay, and then at the front, we need to put a number because this isn't the only way that I could get 6 heads. I could also go head, tail, head, tail, head, tail, head, tail, head, head. I could go 4 tails at the beginning and then all tail heads at the end. So there's many ways. So I need to write a number at the beginning for how many ways I can get 6 heads and 4 tails. So that's out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. I'm trying to choose 6 of them to be heads. And this would be the same as 10 choose 4. I could also do 10 positions. I'm choosing 4 to be tails. You get the same answer. And then you just plug this into your calculator. And you'll get the probability. Oh, let's do that together. Take out your TI-83s. So it's in your math menu. Then put the left button. You get probability. And then number 3 is and choose R. So first you need to put in the number 10. Then math, probability, number 3. Then the number 6. We want 1/2 happening 6 times. And we want the tails 1/2 happening 4 times. Ta-da! The probability is 21%. So you put in the n first. Yeah. First you write the number n. Then you go to the math menu. Go to probability. Choose number 3. Then the R value. 1/2 happens 6 times. And 1/2 happens 4 times. 21%. Are there any questions about that? Did you guys learn another way to find that probability last year? So there's also something called a binomial PDF. We'll go over this next week as well.
PDF? Is it a PDF file?
It's not like an Acrobat reader.
Oh.
But if you go to your catalog, or I think it's in the math menu as well. Nope. Distribution. There it is. Binomial PDF. There he is. The arguments of binomial PDF are just NPX. So I put in the number of trials, comma, the probability of success, comma, how many successes I want. I want 6 heads. That should give me the same answer, crossing my fingers. I haven't tried this. Yes. Okay, so usually I find it from the catalog. The catalog has everything. Second 0. And then you just push the letter B. So letter B is the apps button. And then it gets you to the binomial PDF section. I'll write it down on the page. So you can also use binomial PDF, and the arguments are NPX. CDF or PDF makes a huge difference. No, it doesn't matter which one you use. This will just be faster. Yeah. I'll tell you that next week.
There's a catalog. That's crazy.
So the arguments for the binomial PDF are the number of times you're repeating the trial, the chance of what you're getting, the chance of success, and how many successes you want. So we're tossing a coin 10 times. The chance of getting heads is 1/2, and we want 6 heads. That gets you the same answer. And you can also use this for those problems where you have like expanding a binomial. These sorts of questions. It's just a shortcut. But usually I forget the order of the letters. Like I forget, does N come first? Does P? On an exam situation, I totally blank. Then that doesn't help you much. So it's better in some ways to know this formula, so at least it's given to you on the formula sheet.
But it asks for like, oh, how many trials you want, right? For the binomial PDF.
No, it doesn't say. Yours does?
Yes.
Oh, some calculators ask for number of trials and stuff?
Yeah. See.
Oh, no fair. Nice.
It's awesome.
Brian? Yes, Elliot. Can I show the first method on the calculator one more time? Oh yeah, sure. So first you do 10, then you go to your math menu, and you go left 1, and you choose number 3, and then you write the number 6, and then 1/2 to the power of 6, 1/2 to the power of 4. So that's a step-by-step way to get that. And if you miss that, you can also watch the video on YouTube and just fast forward to this part and watch me plug it into the calculator and follow along with it.
And subscribe.
So, the chance that a particular page in a math book contains an error is 20%. Find the chance that 12 pages in the book, out of 12 pages, 4 of them contain a misprint.
That's a terrible math.
So, to build this, again, we start with, basically I usually start with the model. I want misprint to happen 4 times, and then normal print to happen how many times? 8, because I've got 12 pages altogether. If there's 4 misprints, that means there's got to be 8 properly printed pages. Does that make sense? Okay, so each of the misprints is going to be 0.2. And what's the chance of getting a printed page right? 0.8. So each of the printed pages is going to have a 0.8 probability. So that means I have 4 0.2s because I've got 4 misprinted pages. And I have 8 0.8s because I have 8 properly printed pages. Okay, and then I just need to put in the number at the front that tells me how many ways I can rearrange all those letters. They can only do no calculator ones if you're able to draw Pascal's triangle. So it would have to have really small numbers like 3. And usually you can solve that with a tree, just like we did the tossing the coin problem. Yeah. Right, good question. So how do I know this probability is 0.8? There's only 2 choices. I can either print it wrong or print it right. If printing it wrong is 20%, printing it right has to be exactly the opposite of 20%. Yeah, 0.2 times 0.2 times 0.2 times 0.2. Each single event is equal to 1. It's not like this whole thing has to add up. Yeah, there you go. So the number of ways that I can rearrange those is the number of positions I have. Thank you. I know my virus protector is kind of worn out. I'm trying to choose 4 of them to be misprinted. Okay, so now if I plug that into the calculator, I'll start with the n value. N, math menu, choose 4. 0.2 is happening 4 times. 0.8 is happening 8 times. I get 13% chance. Okay, or I could go to the catalog, to the B section, and choose Binomial PDF, 12 trials. The chance of getting a misprint is 0.2, and I want to get 4 misprints. Same answer. So I'll write that down here too. Binomial PDF, 12 choices, 0.2 chance, looking for 4. Go ahead. Yeah, try the next one on your own. Okay, so I'll show you a little bit about what goes on in my head when I solve a problem like this. I want either one misprint or no misprints. And I'm going to add up those possibilities. So that's 12 pages. Choose one misprint. I want one of the 0.2s and all the rest of the pages 0.8. So you notice that the two powers will always add up to the total. No misprints is 12, choose none of the pages. I want 0.2 happening no times and 0.8 happening all 12 times. Now I want to know how many ways is that. I can do this one without my calculator because if I only have one misprint, that M can happen first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, or 12th. There's 12 ways that I can put that M there. There's 12 spaces where I can put that M. So I know 12 choose 1 is just 12. And 12 choose 0 is just 1, because there's only one way that I can have all P's. So to plug this in easily without having to use my choose, it's just 12, 0.2, 0.8 11 times, and 0.8 12 times. Which is 27%. Oh, that's different from what you guys got. Oh, no, I don't have plus. No, this should be right. Oh, okay, you just rounded it. Okay, for the last example, this is a little bit complicated. I'm going to need a tree. So you have a bag. A counter is just like a little circle thing. You got 2 red little circles and 3 green circles. And you're pulling 2 of them from the bag without replacement. So first we're going to find out the probability that we get 2 green counters. So we'll just pretend that we're taking one at a time. So the first counter and then the second counter. So the first counter could either be red or green, and then the second one could be red or green. And the chance that we get a red one is 2 out of the total. And the chance that we get a green one is 3 out of the total. Now if we take out a red one, because we're not replacing it, we'll only have 1 left. So the next probability is 1/4 for red and 3/4 for green. And those are conditional probabilities because they depend on what happens on the first trial. If we took out a green one, then the chance for red or green on the second pull is 50-50. So the chance that we get 2 green counters is this branch. 3/5 times 1/2, or 3/10. So now we're going to repeat this experiment many, many, many times. And that's what makes it a binomial. So now we're going to take 15 trials. And each time we take out 2 counters, we'll put them back again. And we want to know what's the chance that more than 12 of those trials that we get exactly 2 green counters. So that sounds really complicated. But basically we're repeating this experiment 15 times. And we want to get 2 green counters at least 12 times. So that means we get 2 green counters 12 times, or 13 times, or 14 times, or all 15 times. And we're going to add up all those probabilities. That sucks. Next week I'll teach you a shortcut. The trouble with the shortcut is usually, again, it's just like the NPX thing on the calculator. Usually on a test situation I forget the order of like NPX, and then I have to go back to the old standard method anyways. And in math, if you can solve a problem 2 ways, then you'll really be able to tell your answers right. So we've got 15 tries, and we want to get 12 green ones. The chance of getting 2 green is 3 out of 10, and we want that to happen 12 times. So now you just need to figure out what goes in the other bracket. Okay, or we can have that happen 13 times. Or we can have that happen 14 times. Or we can have that happen 15 times. So we need to figure out if we're getting success 12 times, then what's the chance of failure, and how many failures are we getting? So if we have a 3 out of 10 chance of getting 2 greens, what's the chance that we don't get 2 greens? 7 out of 10. It's exactly the opposite. And if we get 12 green ones, then how many non-green ones do we get? 3. These 2 numbers here will always add up to the total number of trials. So we get 12 greens, 3 not green. If we got 13 greens, we'd have 2 not green. 14 greens, we'd have 1 not green. And 15 greens, we'd have 0 not green. Now is the fun part.
It's really small.
Yeah, it should be really small. We should have a race. Who can do this the fastest?
Using the shortcut key.
No shortcuts.
Is the shortcut way the computation thing?
Yeah, that's right. Well, kind of. Does anybody know what 15 choose 14 is? It's the same as 15 choose 1. It's just the number 15. Yeah?
Oh.
We're using the probability 3 times because
What's that?
and so in the first part we found the probability that all the 3 times right. The second part it asks does 200 replace at each cross? That means
We take 1 and then take another without replacing, but then we replace them both. And we repeat. Take 1 without replacing, take another, and then repeat. It's a very complicated question. So your homework for today. Oh, Johnny, did you get the probability on that one?
No, I did.
Oh. Your homework for today comes from page 533. Numbers 3, 4, 6, and 7. Okay, so if you have trouble with plugging that into your calculator, just watch the YouTube video over the weekend.